Hi, today we will discuss the classic graphic statics. First, you will see why should I discuss this one. Anyway, I will give you some motivation. First, diagram, Maxwell's diagram, and more examples. This is a beautiful rope truss for a convention center. If you only do it by hand, it seems like this is impossible. So you need a computer to do this. But think of it. This is the product of graphic statics. The use of graphic statics grew from the 19th to 20th century, but take note, lost popularity due to the emergence of computational analysis methods. However, being an intuitive method of visualizing form and forces, graphic statics has recently seen an increase in popularity. So for this particular structure, we used, or the authors actually, use graphic statics to optimize the structural system, in particular the truss system. Here is the form diagram, original, and then the force diagram, and then the normalized volume. As you can see, the diagram has a 45 meters cantilever on one side and 27 meters cantilever on the other side. The midspan has 90 meters. So you can see the first diagram using the graphic statics in the second column. They normalize the volume and it decreases as they change the form. And here they were able to find the shape. It's almost like the wing of the airplane, but the volume is still 0.852. But if they change some of the wave members, suddenly the first diagram changes. So with the normalized volume to 0.669. So this is quite an optimized roof truss using the graphic statics. So here we have to go back to example 5.2 of Seaward. We talk about this one by scale drawing, or we want to compute this truss using scale drawing. So here we computed the force P. We have shown this one before, and here we will have to discuss first the force triangle. Actually, you have discussed this already in your statics of rigid bodies. I just want to review this again, but I hope last time you were not able to really appreciate the method, but by here I will try to let you really appreciate the method, because the method is quite intuitive and it's quite good in visualizing forms and forces. The same problem which we solved for the method of joints can even be solved more easily and quickly using scale drawing of vectors of the forces which is meeting at point A. The length of its line is drawn proportional to the force, so a suitable scale must be determined. The vectors are drawn parallel to each other, starting with the known value. The magnitudes of the two unknown forces are determined by intersection. So even if you have two unknowns, you can find its value by along its intersection. So starting from its end of the known force vector, draw lines parallel to the two unknown forces until they intersect. So what does it mean? You have to draw your structure in a scaled manner. You have to scale it, and then with that drawing, you can just draw the forces parallel to the members of your structure. The fact that the vectors form a closed circuit ensures that equilibrium has been satisfied. So as you can see, we have this structure. It's quite beautiful because the force or the weight 1 kilonewton is being uh, pulled by this girl at point B and being pushed by this boy at point C. So here the weight 1 kilonewton is going down, and the tension force from A to point B is here, and the compression force from A to C is also written here. And if we have to scale these forces, assuming that 1 kilonewton is equal to 2 centimeters, so by drawing, the 1 kilonewton will be equal to 2 centimeter. And then you can draw the compressive force and then also the tension force. The intersection, the two forces will intersect actually. So after intersecting and closing the circuit, then you can now measure these two forces using the scale 1 kilonewton is equal to 2 centimeter. Careful scale drawing provides sufficient accuracy for structural design, and the likelihood of mathematical slips is reduced. So actually it's not really necessary that it's very accurate uh, to for the process of the member. So you don't need to have a very accurate result, because even using scale drawing is sufficient for the accuracy of structural design. A proper drawing board should be used when doing this method. The starting point is an accurate scale drawing of the structure, like the structural model on the right. The joints must be considered in the same order as in the previous approach. That is, not more than two unknowns at the joint under consideration. The procedure is to draw a first triangle or polygon for each joint. A suitable scale must be determined. In this case, 10 kilonewton is equal to 1 centimeter. So here, what we are going to do is scale drawing of a vector diagram for each joint. And since we will be looking for two unknowns at a joint, so we will be using joint E first. So for joint E, we have this forces we assumed last time in our example, and we will be using it starting from the known force, that is the 10 kilonewton force. Again, the scale we use is 10 kilonewton equal to 1 centimeter. So by drawing 1 centimeter down from this portion down, that is 10 kilonewton, and starting at the head of 10, you can draw the horizontal line, this one, from the head. Just copy this one horizontally going to that direction, or you can also draw in that way, because after that the second force should be applied either there. This is not possible because this should be parallel, so it should be in that direction. Okay, so look for the intersection of the two lines, and after that you can measure this distance, because this represents the force FED. So in this case, this is around 1.5 centimeter, so which is equal to 15 kilonewton. Also, you can measure from this intersection to the tail of the load 10 kilonewton. That's around 1.8 centimeter times 10, so that's 18 kilonewton. Also for joint D, this is much simpler because we already have two known values. 10, you can start 10 if you want, and then going that direction for this force, and then another 10, you can write there, because this is 15. Of course, the FDC is not yet known, but you can just draw this way and draw FDP horizontally. Of course, this is a rectangular section, so the result will be the same. FDC is equal to 10, and FDB is equal to FDE, which is equal to 15. For joint C, as you can see, there are four forces with different inclinations. We have one horizontal, two vertical, and two inclined forces. So again, starting from the known force, that is 10 kilonewton FCD, which was calculated earlier here, and then FCE, you can try in that direction because that is tension, and then of course you cannot just draw here, so you have to go to the other portion which is known FCE. Here you can draw FCE parallel, and that is tension, and of course FC is 18, so you know that this is the end, and then you can draw FCB parallel to the, here you can draw the FCB parallel to the member FCB. So check the intersection of FCB and FCE. Okay, so this is the end of the force. FC and the beginning of the force FCB. So after that, you can measure the distance in how many centimeters. Probably this is 3.9 centimeter times 10, so that's 39 kilonewton. Also here, you can measure in terms of centimeter, that's 3.12 centimeter times 10, that's 31.2 centimeter. And lastly, the reaction. Uh, it's quite simple to draw the reaction because you can have the joint B. We'll look for joint B. Where is joint B? Here. This is joint B. So there are one, two, three, four forces. So with that four forces, we have FDBD, which is calculated earlier, and then we also have FBC, which is calculated earlier, and then you can draw the vertical reaction and the horizontal reaction here, and then you can measure the distance. Maybe this is 2 centimeter times 10, so that's 20 kilonewton. Also, we have to measure this distance. Probably that's 3.9 cm times 10 kilonewton, so that's 39 kilonewton. And to determine the resultant of RBH and RBV is simply draw a vector from the starting point of RBB to the end point of RBH. That's the resultant, which is RB 44.7 kilonewton. And of course, you can also measure the angle or the direction of RB with respect to the horizontal. So here is the summary of the forces uh, computed using scale drawing. So actually, it's quite easy to use this one, but of course, since we draw the polygon in every joint, it makes the problem or the solution tedious. But actually, we can just directly draw the whole structure because here we just introduce the equilibrium of polygon for every joint. But the problem is that there will be some duplications. So in the other method, the composite force diagram, or what we call the Maxwell's diagram, this is much easier to use than the previous one. In this graphical method of joints, the vector for its member needed to be drawn twice because it was included in the force polygon at both end joints. With composite force diagram or the Maxwell's diagram, this is not necessary as all of the joint resolutions are combined into one diagram. And to prevent confusion, it is necessary to adhere to a convention known as the Bose notation. This can be explained in the following example. Here we have the diagram showing the numbering of Bose notation. Normally it should be done in a clockwise manner. So if we say between the force, this should be between the forces and the members. So between the force here at B and A, we have 1, A to E, we have 2, E to D, we have 3, then D to B, we have 4. And of course, it's not necessary to add number here because there you can just there is only one force here, and of course at the middle, and there is no member here actually. So 4, next is 5, and then 6. Member CE is actually 2, 6, or 6, 2. The first 10 is 2, 3, or 3, 2. And then member DE is 3, 6, or 6, 3. So that's how we number it so that there will be no confusion in the drawing. So here we repeat the analysis of the truss using a composite force diagram. Again, you have to draw a scale drawing first, just like this one. So for step 1, you have to number all the spaces between the members. So here, since there is no member on AB, this is just confusing. I hope you remember there is no force here, member here. So you have to number all the spaces between the members and the external forces and reactions. Its force can then be identified by the two numbers on its side of it, as I mentioned earlier. Although the direction of the reaction at point B is not yet known, it can be added approximately at this stage. Number 1 covers the whole space from RA to RB here as far as member BC. The number 2 covers the whole space between RA to the load A here. And the force 1, 2, this is force 1, 2 here, the member AC, this is the force 1, 2, therefore represents both RA and the force in member AC. In step 2, again starting on a joint with only 2 unknowns, that is joint E in this case, draw the force polygon to a suitable scale. Add the numbers to define the force by working consistently clockwise around the joint. So here, if we have to draw the force 10, because we know the force 10, again you have to use scale. If we assume 1 kilonewton to be 1 centimeter, so you can draw 1 centimeter, 2, 3, so 0.23, and then the 3/6 is horizontal, so just copy horizontal, and then the incline member to 6, which is connected at the tail of 3, 2 here. So this is a closed polygon of the joint E. The non-force 10 kilonewton is drawn first, going clockwise around joint E. So clockwise is the procedure. And force 2 to 3 is 10 kilonewton downward. So therefore, point 3 is shown below point 2 on the force diagram. The force 3/6 represents the force in member DE, and it can be seen that on the force diagram, point 6 is to the right of point 3. Therefore, the direction of the force in DE is to the right. This arrow could therefore be added to the diagram of the structure close to E, thus indicating that member DE is in compression. Step 3, moving on to the next joint with only 2 unknowns, that is joint D. The forces are now added to the same diagram. So from joint D, we have 3, 6, and then the force 10 is 3, 4. This is 10 going down, 3, 4, and then the member DB or 4, 5, that is horizontal, and then 5, 6, which is vertical, 5, 6. So this is the complete diagram for joints E and D. So with joint C, you can add joint C. Here we have 5, 6. So 5, 6, and then we have uh, 6, 2, 6, 2, and then 2, 1, that is horizontal, and then also uh, 1, 5, 1, 5. Yeah. And then after that, you can take the intersection. The force, this 4 to 1 is the reaction at RB. So step 5, from figure D, it can be seen that the force 4, 1 represents the reaction at B. Its magnitude and direction can therefore be determined. Step 6, again, the reaction should be checked by taking moments for the whole structure as in example 5.2. So this is now the complete Maxwell's diagram of the, the example. The magnitudes of the forces can be scaled off from the diagram, and the directions of the forces determined either by inspection or by the method described in step 2. So, of course, as I have said in step 6, you need to check your work by taking moments for the whole structure. Here are other examples. The classic example is the arc structure. For one element, we use a force polygon to complete the equilibrium of this element. But for the whole structure, this is the force diagram. And the portion of this one, this is for the element. Another example, a Warren truss. As you can see, if the Warren is loaded at the bottom chord, this is the composite force diagram of it. You can try by yourself. For the inverted Howe truss, which is loaded at the top chord, this is the force diagram. For the Pratt truss loaded at the top, as you can see, here is the diagram. And so with the prop truss loaded at the bottom, as you can see, this is the force diagram. And of course, it also draws the tension forces, which is red, tension members, and the compression members in blue. Again, don't be confused with it because I'm used to use blue as tension, red as compression, but here in our example, I just took this from the internet to use the opposite one. So that's why I'm saying it's just a notation, and you have to be careful with that one. Also, for the structural optimization, this is not an easy structure. You cannot. This is quite difficult to compute manually. So by drawing with a scale drawing, you can just use Maxwell's diagram to determine the forces. So as you can see, you can optimize the sections by simply drawing it, and you will see the corresponding forces involved. And lastly, for this diagram, a curved truss, as you can see, can also be optimized using the graphics statics. I hope you were able to to see the beauty of the graphics statics or graphical method in solving the different process of the structures, or using this one for structural optimization. Thank you for that. Thank you for listening.